All right, I'm good. I'm ready to go.
Yep.
All right. Hey, good morning, guys. Welcome to OSI's first webinar. I am Shivani Vyas. I'm a technical services engineer with Odessa Separator. I've been here for about 3 years, and today with me we have also.
Hey guys, my name is Donovan Sanchez. I'm also a technical services engineer, and I've been at Odessa Separator for about a year.
Right. So we really want to take this opportunity at this time and place. We all know we're going through some unprecedented times, and we'd really like to connect with you and make a use of this opportunity, and thought we'll just discuss about some of the bases of sand control. And so what we're going to do is going to make y'all understand how do we decide on what is critical for sand control, trying to understand what is the process of homogenization, and then see how can we have that sand control placed effectively in the wellbores. So yeah, welcome to OSI's first webinar, and let's get started. So whenever we're talking about sand control, it is really critical to talk about the frac sand. So Donovan, if you want to go next. Let's go ahead and guess how much sand does a average well in the Permian Basin, or the frac sand, does a average well in the Permian Basin need? If y'all can go ahead and type your answers on what is it. Either it's 8 million, it's 12 million, is it 18 million or 25 million? We'll give you about a few seconds to go ahead and answer that. Okay, so let's understand this. Donovan, if you want to go to the next slide. Let's go ahead and understand this. Back in 2015, the laterals or the horizontal wells, the laterals were about 5,000 foot, where it's gone to 8,000 foot by 2018. So the graph on the right-hand side is going to show you how much pound of frac sand were we using per lateral foot in 2014, which was less than 1,000 pounds, has gone up to more than 2,000 pounds in just 2018, in just 4 years. So we're talking about less than 1,000 pounds to about 2,250 pounds of sand per lateral foot. And now, if you're imagining an average well in the Permian Basin, the lateral is about 8,000 foot. So we're using, per well, we're using 18 million pounds of proppant sand per well. So Neil, you were off by just a little bit. It's about 18 million pounds. And imagine this is just one well. Now, the graph on the left-hand side, we can see how many wells are drilled and are uncompleted. So this is what we can see by the basin. And if you see the graph on the very end, obviously has to be the highest in the Permian Basin, is about 3,722 drilled but uncompleted wells. Only in those wells, which are even uncompleted, we're needing about almost 67 billion pounds of well to complete those. So let's go ahead and see, as far as Permian Basin goes, how big is the production of sand? You want to go next, Donovan? So imagine this, we're producing about 2.8 million barrels of oil per day, and just in the Permian Basin. And we're using about 37% of US's propane demand. If we were to compare this to how many tons of sand, we're talking about 68,500 tons of sand per day, which means we can fill up to 600 rail cars. That's insane. And if we're to combine this, we are more than the next two largest basins, which is combined of Eagle Ford and Marcellus or Utica. So that's what it is we're estimating an average by 2022, it might be up to 111 billion pounds of sand that we'll be using just in the Permian Basin. And regardless, some of the counties or some of the formations in the Permian Basin, like let's say the Wolfcamp Horizon, still uses about 5,000 pounds. We were talking about 2,250 pounds per foot lateral. Here we're doubling up the numbers right now. And in the Wolfcamp formation, we're using up to 5,000 pounds, which means we're averaging to 13 million pounds of lateral foot of sand. So when we're producing this much sand, since we are injecting this much sand over the period of time, there is no doubt that we are going to produce this much sand. And that's why it's important to understand that why are we going to have that much sand production?
Okay, so what do you think some of the issues would be if you just go straight into the well with an ESP with no sand mitigation tools and you're just going straight in, your pump's going to be pumping all that sand that Shivani just described is in just a single well. With an ESP, you may see one of a few issues, from plugging issues and you're seeing your impeller clogged from just there being too much sand. And also, how does an ESP work? It's continuous. It's running 24/7. It's not going to stop. So all that sand that's getting in the pumps and the intake and the impellers just continuously hitting the sides of the tools and or the side of the ESP on the outside, you're going to start to see some erosion. And that erosion can lead to some broken shafts. It can lead to erosion on components. As you can see in the picture in the top right, some of the components that may be damaged more quickly is some of the cables on the outside. And no one really wants to deal with the grounded ESP just because your cable has been eroded just from the sand. So I believe there's some things people need to take in consideration, especially in a new well that's pumping 24/7, that you need to install some type of sand mitigation tool down below. And ESP is not the only tool that you're going to be seeing some of these failures due to sand. The SRP is also can be very susceptible to sand failures due to the rod buckling. The rod buckling happens when you see that sand getting stuck on top of the pump and causing friction and buckling. And then that sand can also cause vibrations in the pump. So what you can see from the thermometer card on the right, that's like what a typical card may look like. That may give you an idea of well that has high sand issues, because you can see the vibration and the peaks and troughs of that card. So when you're seeing that, you may see a rod buckling failure in the future, and that just leads to more capex that no one wants to deal with. You don't want to deal with the workover. So people may just want to start considering some downhole mitigation tools. So what are some of the tools we see existing on the market today? Well, there's a few different kinds. I'm sure people are pretty familiar with the desander, bottom middle. There's a lot of desanders on the market. There's also different types of screens. There's our mesh wire screen, and then our premium mesh wire screen right here in the center. We can also have different types of plungers that are designed for sandy wells, such as the FARR. It just helps trap the sand and then expunge it. And there's also some valves that can help with sand mitigation. But all of these sand mitigation tools will have their upsides and their downsides. So you really have to take into consideration what type of problems your well is having and what type of other problems you may come across. So that will help you choose and what type of technology you want to go with, whether it be desander, screen, different type of plunger.
Right. So that makes it really critical, like Donovan was talking about, how can it affect especially two of the dominant artificial lift systems in the Permian Basin, and what criteria leads us to choosing what are our critical tools for sand management. And if you see, this is a table where it shows what can we do as far as keeping the sand downhole and what can we do once the sand is produced. Since we have experience on the downhole conditioning, we're going to go ahead and go in detail about what we say on keeping the sand or having the sand distribution efficiently downhole. So all that consists of your sand sieve analysis or sand sieve distribution, your chemical stability, mechanical well conditions, and then obviously your production conditions. So we'll go ahead and see the first is, like we can see, is the sand sieve analysis. If we see the graph right here is what is exactly is telling us the sand size distribution. So let's say we've taken a sand sample. We've gone ahead and gone to the lab, dried it off, because we do know that the sand is accumulated with your oil and water. And once we dry it, we'll go ahead and have the sieves of different sizes, which means that the particle size that it collects the most will have a number, and that will lead us to coming up to a definite slot size. So in this graph, we can see that some chunk of the sand particle sample that we have is a 50 slot, and most of it is pan sand, which means that it is fine particle. And now we are talking about so much injection of frac sand, which is a combination mostly of 40, 70, and 100 mesh. So no doubt, most of the sand particle is going to be the pan sand or really fine particle sand. So that gives us the basis of, okay, this is the distribution of my sand particle size, but this is not an immediate decision of that this is going to be the slot size. It definitely gives us an idea that there is an optimal range of the slot size, what we're going to select. But what comes into the consideration is what is the water cut. In the Permian Basin, we're talking about anywhere to 60 to 80% of water cut. What is the sand production? Is it the initial stage of the production? Are we talking about the ESPs, where we know that the first 3 months are pretty critical, where we've seen just in the pictures that Donovan showed us is just the plugged intake? Is it a lot of chemical? If we're talking about the Martin, Howard County, is there a lot of iron sulfide, a lot of corrosion that comes into consideration? How well or where is the perforations in this well? What is the deviation and the inclination of the well? All that comes into place while we're deciding what is the optimal or effective sand control technique that we're going to use in a particular well. Also, another critical thing is the particle size distribution. Now, when we're talking about, yes, I need a solid control tool and I am injecting 40, 70, 100 mesh, which means it's like a fine powder sand. We've heard it more than 100 times, right? And I need the tightest slot size screen to go ahead and filter out all those sand particles, right? I believe that's where we're exactly wrong, because just this sand particle, we can see the 250 micron that is dried is such a fine particle size. What happens when it goes downhole? It goes ahead and agglomerates with your oil and fluids of the well, which means that it swells up. And that is exactly your 250 micron goes ahead and becomes the size of this. And imagine if this gets stuck outside the screen or the intake to the pump, we are not going to be able to produce anything. And that's where we're going to be seeing all your pressure drops go down. So how effectively can we distribute the sand particle size, or what can we do to go ahead and have an efficient production while we're having such a huge sand production problem? So one of the technologies that we're going to go ahead and talk into detail is homogenization. What do we mean by homogenization? Just like the term says, it goes ahead and homogenizes the fluid. But the question is how, right? So what we're doing is we're using a screened system, which means that it effectively distributes and solubilizes your sand particle size using the entire wellbore. That way, the sand slugs that comes in does not go directly into the pump, but goes ahead with different parts and goes and distributes evenly in the wellbore by using couple systems or just a single system below your pump. Now, understand that this is nothing to do with the pump intake. It does not change your pump intake. In the wellbore diagram, just on the left-hand side, we can see an example of an ESP. It still has its own intake, but what we're doing is we're going ahead and including an intake below. That way, it efficiently separates or homogenizes the fluid before it goes ahead and enters your pump intake. That way, it gives the sand in batches just what the pump can handle.
So how do we choose our screens? How do we choose a slot size? And how do we choose how many different screens we will need in one bottom hole assembly? So for starters, slot size is the first main thing we'll take into consideration. Like Shivani said earlier, we will do a sand seal analysis so we can see the particle size distribution, so we can get an idea if we're either going to try and filter out some sand or we're just going to do some homogenization and just try and distribute that sand more evenly, because as you saw in that picture before, even though the 250 micron sand is, when dry, it's really small, it can still glutinate together and become slugs. So that's one of the main benefits of the homogenization, is breaking apart that sand slug and just helping it get into the pump and more easily, and so it doesn't take it all at once. It can handle it a little bit more easily. Another thing with slot size is we want to make sure we don't have paraffin in this well, because paraffin, if you're choosing a smaller slot size, then it will start to plug up the slots more quickly. And scale will also do the same thing of plugging up those slots more quickly, and that's just added issues that we don't need. So that's another factor we want to take in if we're just going to want to go with homogenizing the fluid instead of trying to filter something out. And lastly, for the slot size, we can also just take a look at the failure and pull reports, just so we can see how often they're having a pull and how often it's failing due to sand. Secondly, we want to take in the length of the assembly. So velocity is an important factor we need to take in, because we need to make sure the screens can handle the velocity going through. We want to make sure our screen will hold up and it'll keep its integrity throughout the runtime of the well. And also, if the velocity is higher than what we think the screen can handle, then it's not really going to be doing its job. Everything's just going to be going through quickly. So that's the first thing we want to take into account. And the second thing is the pressure drop. So this is where we would want to add more than one or two screens if we're going a little bit tighter on the slot size, because if you're going really tight, then you're going to start creating a pressure drop, and then that will start to create scale. And that's just a different problem on top of a problem we're trying to solve. So yeah, you're trading in one, but then you're just creating another problem. So that's also something we want to take into account, because we don't want to create a problem that's unnecessary. So here's kind of an idea of how we like to do our screen selection for the length of our assembly. So some of our input data is fluid production. So right here, this is something typical you probably see in an ESP, about 4,000 barrels of fluid per day. And like I said earlier, it's running 100% of the time. And this tubing screen is 24 feet, and we're playing around with the well classification, which is average. And if you look at the table to the right, the sand production, we like to go by ppm, or parts per million. So average, we're seeing 11 to 50 milligrams per liter of sand production. So that's where in this well. So that's kind of what we're going to classify this well as. And then we put the number of tubing screens right here. We go 7. So with all this input data, fluid production, screen diameter, slot size, well classification, we're going to get our output data, our fluid velocity compared to our critical velocity. Our critical velocity is the velocity that our tubing screen can handle. So the main focus of this is trying to get the fluid velocity per second through the screen lower than a critical velocity. So as you can see here in this example that we put together, this fluid velocity is quite a bit lower than our critical velocity. So we want to keep a safety factor as well, just in case some well characteristics change or something unexpected happens. You just always want to keep that safety factor in consideration. Next, we want to calculate the pressure drop through the screen because, as I said before, we're not trying to create more problems than we already have. So we're doing this to make sure we're not going to start creating scale in the well. So you can see here is our calculator. Like we like to play around with well characteristics. Our input data will be our slot size, diameter screen, our fluid production, our API, and our standard gravity, which in the Permian Basin is not as big of a factor since everything is usually around the same API. But let's say you're in North Dakota or Canada, then you're going to start getting a little bit of different APIs. So that's when it becomes more of a factor in including this, along with our fluid viscosity thing. And then our output data will get our total pressure drop through the screen right here, 0.09 PSI. We're trying to keep this as close as possible to zero. So as you can see right here, 0.09, we're doing pretty good right here. We're not creating any extra problems. Next, when it comes to selecting our slot size, here's something, here's like an example of a sand sieve analysis. On the left, you can see on the left vertical axis, it's charting the retained weight. And on the right vertical axis, it's charting the cumulative percentage. And that cumulative percentage we will be using right here with a D number. In our case, we're using a D10. So that's the cumulative percentage of 10% on this equation right here. So generally, if we're going in blind, we don't really have too much data. We'll just say 3 times D10. So that means we will choose a slot size of cumulative percentage of 30% because, as Shivani said earlier, we're not really trying to filter out everything because then that just creates more problems. So right here, we will just try and filter out 30%. So if you see right here on the vertical axis, we have 30% right here. We go to the left and we'll see where this crosses the axis. So everything to the right of this will get filtered. So as you see, we're filtering out everything smaller than 381 microns. Now, if we do have well conditions and a failure rate, this is where we can take a more calculated slot size recommendation. So if the failure rate's like 3 months or less, we would go 2 times D10. So if you look right here, 20%. Now we're filtering out everything greater than everything to the right here. So just from decreasing our D size, cumulative percentage that we want to filter out, we're going to filter out a lot more of the sand because we're trying to solve more of the problem. But the less frequently the failure rates start to happen is the more we start to loosen up our slot size. So from here you can see 3 to 6 months, we like to go 3 times D10, and failure rate above 6 months, we'll go 4 times D10. So 30, like I said, we'll filter everything to the right, and then 40%, now you're filtering out even less. So at this point, you're starting to see a little bit more sand going through, but it will still have that homogenizing effect of breaking up those sand slugs and while still filtering out a little bit of sand.
All right. So since now we get a little bit of idea of how do we select the screen sizes, let's go ahead and go into a little bit of detail of how does the two-stage separation work. Like Donovan mentioned before, we have some of the existing tools in the industry that industry is familiar with is just using a one-take or one-stage intake system just to go ahead and filter out sand. But since we've seen that when the failure rate is less than 3 months or just in a few days, we do know that we're producing so much sand that it's critical at this point to go ahead and have the homogenization or control and distribute your sand evenly. So how do we do this is we have your sand screen. that is just not one of the regular ones. It is a V-wired screen, which means that the wires are in a shape of V, and then it has either a stainless steel 306 jacket or it has 316 stainless steel jacket if there's to do a lot with corrosion. And right below it is what we have the vortex sand shield, or what the industry is familiar with is a desander. So what happens when we combine these two? You have a combination of sand. Yes, we are inducing a uniform sand, which is your frac sand. But what about the reservoir sand? It's still going to be there. We're talking about all the sandstone formation, all the tide formation, the shales, the unconventionals. So it's always a combination of the uniform and non-uniform sand that we're talking about. And that's exactly where we need to go ahead and distribute these two evenly. So when we do know that your sand sieve analysis does show that this is your distribution, which is always a combination of your bigger chunk and your smaller chunk of particle, we go ahead and have your intake to go ahead and have all those factors come into place, like Donovan mentioned, is your velocity of the fluid, your pressure drops, and then below it, you have mainly three things that come into consideration is your helix that creates your centrifugal force, your sleeve, just in case we're producing so much sand that whenever we have a cutting of the body, there is still an external protection that you do not have the loss of integrity of the tool, and now you do not have a fishing job. You still have your filtration and homogenization going on, just in case you have that sand cutting or cutting in the wellbore itself. Another thing, what separates on the two-stage filtration, if you go next slide, Donovan, is exactly here. We're saying on the one-stage filtration is how quickly are we filling up the tailpipe, and now what we know is all those pump parameters that we are going ahead and increasing that pressure drops. We are not producing just because we are filling up the tailpipe as soon as possible. And now what you have is in well intervention. Versus on your two-stage filtration, what you're using is you're going to go ahead and distribute the sand evenly. You're using not only your tailpipes, but you're using the entire wellbore to go ahead and distribute the sand. And this is something that is really critical to understand, that when we have so much sand, there's no way we can go ahead and just disappear the sand. The important thing is how do we utilize the entire wellbore? That way we give up the pump as much as it can handle. So that's what gives you more runtime, gives you the production that you need with the optimal pressure drops and with the optimal fluid velocity that the well can handle. So going a little further into your first stage filtration, depending on the sand sieve analysis, in this example, we can see that you have all your bigger sand size, which is you can see on the horizontal, we have the slot sizes, which is your 50 slot, 30 slot, 20 slot, 15 slot. And depending on this size distribution, we will be able to go ahead and filter out the bigger sand particle, which means, let's say that this is your sand sieve analysis, and you do have your largest size volume is your 50 slot. Now, again, we got to go ahead and understand that this is the dry sand we're talking about. So how about once it goes ahead and accumulates, what happens? So it is something that we need to keep in mind that, okay, let's go ahead and open up that slot size. Probably in this case, we might have to go with a 75 slot size of the tubing screen, because in this case, it's really important to go ahead and homogenize. Whereas when we have a 15 slot that comes up highest, we can go ahead and go with a 20 or 30 slot, again, depending on the well condition and what is the failure rate. And then your second stage, like I mentioned before, takes care of your minute or fine sand particles, which means that all your finer particle is going to be separated whenever the vortex sand shell creates that centrifugal force by this helix and gets dumped into the tailpipes. So we are, like you can see, we are distributing the sand evenly, we're filtering out, and then we're dumping the finer sand particle. And we did a test on dumping all the different sizes of sand particle and seeing how does the centrifugal force generate and creates that separation. So you can see that we're dumping all kinds of sand. It's non-uniform sand. And you can see the helix itself is stationary. It's the fluid around it that is moving and creating that centrifugal force. So it is really critical what size do we choose on that helix size. If it's an ESP where it's producing few thousands of barrels for the first couple months to few months, it's important that we have that optimal spacing in between that helix. That way it can handle that much fluid. Versus when we're sizing it for a rod pump, which is producing about 500 barrels or 200 barrels of fluid per day, we probably will have to tighten up the space. That way it again has to generate that centrifugal force. That way all the sand particles, like we can see below, is gone ahead and been dumped into the tailpipe. So just to conclude, whenever anybody says that we're going to go ahead and filter out 100% of the sand problems, we cannot do that. That's a lie. What we can do is we can go ahead and distribute evenly. We can go ahead and size accordingly. That way the fluid is homogenized. We can go ahead and calculate on what is the fluid velocities downwards, what are the pressure drops. That way we do not have the plugging going on the intake of the pump itself or the intake going through the pump. What we can do is we can control the frequency of the pump. That way we do have increased runtime. We do have the production that the operator is targeting for. And for all of that, that is something it's really critical to go ahead and analyze what are the well conditions, how much is the sand problem, and then what could it be done so that the well has a effective sand control program on it. And then if you all have any questions, please go ahead and contact any one of us from OSI. Donovan and I are here too. Y'all can go ahead and give us a call or just email us. And if there's anything we can do to help y'all in these times, we'll be more than welcome to do that. And thank you again for the time.
Yes, thank you all for watching.